So, since we have studied about the Newton's laws of motion, we know that in the Newton's laws of motion, the first law of motion we know as the law of inertia. We know the second law of motion as the net force acting on an object should be equals to mass times acceleration, right? Or we also got it
Yes.
that it can also be stated that force is equal to the rate of change of momentum. And in the third law,
Yes.
we got about the action and reaction. But are these applicable everywhere? Are these Newton's laws applicable everywhere? So the answer is that we cannot apply the Newton's laws to all the objects. The point is that these laws of motion, they are applicable only for point objects. If the objects which are there, they are point objects, so they have to be very small with respect to the impacts which are created. With respect to the point of application of the force, the object has to be very small. Then only the Newton's laws of motion work. What if we have a body which is bigger in size? Bigger in size means if we have a body, so for all the bodies we observe that the mass of the body is concentrated at a point inside it, and the whole body is not made up of a single. So yesterday we discussed about the rigid body. Okay. What about the rigid body? So if you consider, suppose you have a body something like this, it's not made up of a single mass. All such bodies, they are made up of, are supposed to be made up of small particles or small masses which are held together. So such a body we call as this is not, of course, this is
Rigid
not a
body.
point mass. We have all the masses scattered in this. All the masses are distributed either uniformly or non-uniformly inside this. So it will be called as a rigid body if on applying any force, you seem that there is no elasticity in this, that it does not change its shape. The shape of the body does not change on applying a force, then we say that the body is the rigid body. So in reality, there is no such perfectly rigid body, but yes, all bodies are rigid to a certain extent and all bodies are elastic to a certain extent. So for this body, if we consider the mass of this body to be concentrated, let's say suppose this is the point where all mass of the body is concentrated. So what name is given to this point? Just what name we give to this point where we observe all the mass to be concentrated?
Center of mass.
Center of mass. So this we call as the center of mass. Inside the body, or sometimes the center of mass may also lie outside the body. So center of mass, it is the point where all mass of the body is supposed to be concentrated, and it will produce the same effects as if it behaves as if whole mass of the body is concentrated over there. So yesterday we discussed, we apply forces at 3 points. What will happen if we apply a force in the line of center of mass? So exactly in the line of center of mass, if we apply a force, a point away from the center of mass, something like this, if we apply a force just below it, so what will the effects produced here be the same? Okay, so will the effects produced here be same? Let's say uh, you have this force F acting on the center of mass. We write it as FCM. Let this be the F1. Let this be the F2. So we will observe, if a force act on the center of mass, this will make this whole body move in a straight line. Hence, a translatory motion will be produced. So due to this force, you will have a translatory motion produced in the object.
Yes, sir.
Now consider here only the force F1. If only F1 acts on this object, so this F1 force will try to move the upper part of the body like this, but due to the inertia, the center of mass will try to resist it. And hence, this body will start rotation in the clockwise direction.
Yes, yes.
A clockwise rotation will be involved. If the force F2 is acting, if suppose you have only the force F2 acting, so F2 will try to rotate this object in the anti-clockwise direction. See, now the forces may be the same. It may happen that the force F1, F center of mass and F2 they are equal. It may happen that all the three forces are equal, but still their effects are different depending on where the forces are being applied. Okay. So
Yes.
the rotational effect which is created in the masses, this rotational effect is dependent on the point of application of force. And hence, this force, this effort which we are putting out to rotate, it is calculated as the rotational force. We call it as the torque. So for this, we calculate the torque. Torque, it is also called as the rotational force. It is called rotational force. And its value or torque can be calculated as, it can be calculated by the formula torque equals Rf sine theta. So R is the distance of the point of application of force from the center of mass. F is the force and theta is the angle between R and F. So for example, if I join this, let's say from the center of mass, I join this. So this would be your R. So this is your R. Let's see. And if you observe the line of action of force is like this. This is the line of action of force. So you have F, R, and the angle between them is theta. So the torque will be computed as R F sine theta. Or there are other ways to write it. We can also write it as R perpendicular multiply F. So R perpendicular means the perpendicular distance from the line of action of force. Okay, but as of now, it should be easy for you to use this formula RF sine theta. Okay. So when do you think that at what angle should the rotational force be maximum?
90 degrees.
90 degrees. Since sine theta is maximum for
Yes.
90 degrees, so torque is maximum. If you want to find out the maximum torque, so maximum torque would be at theta equals to 90 degree. If you have theta equals to 90 degree, you will get the maximum torque, right? Then to increase the torque, there is another way you can try out. It's not only increasing the force. Of course, you can increase the force, but there is another way. By putting in less effort, you can rotate the object. That is by increasing the distance of the line of action of force. So you can increase the distance since the rotational effect depends on distance also. So if you increase the distance, the rotational effect or the rotational force will increase. So this is what we do in the case of wrenches. When we use a wrench to open up a nut bolt, so over there we use the same phenomena. We increase R. From the bolt, the distance is increased so that it becomes easy for us to rotate it. Okay. So that is why you are not able to open up a bolt with your hand, but you can open it with the help of a wrench. Okay. Since the rotational force which will
Yes.
be The rotational force which is required is obtained by increasing the distance, so you get the same amount of rotational. Which, if you decrease the distance, you will need to apply a very large amount of force. So that's not possible. So now we will see this rotational motion in another way. Let's see an example of this we have as the rolling motion. We'll also see how the rolling motion works. So let's see rolling motion. It's an example of rotation only. But along with rotation, you will observe a few other things. So in the rolling motion, what all things we have in rolling motion? Okay. So when you say a substance to roll, so for this, suppose you have this ground, and on this ground I take a circular wheel or any object. Okay. So I put this disc over here, and we will observe how it's rolling. Okay. So since it is a uniform shape, it's a uniform circular shape disc. So where should its center of mass be located? Where should we be able to find the center of mass? The center of the circle?
Yes, sir.
Yeah. So the center of the circle should be the center of mass of the substance. Okay. Now consider any point. So now we consider a point over here. Let's say this is a point P on this disk. Now let the disk rolls rotate like this. So if the disk rotates without slipping, the disk is not slipping, but it is rotating. So if it rotates without slipping, so after half a rotation, I will find this point to be somewhere on the top. The point which was here at the bottom, I had the point P at the bottom. Now the point P will be on the top. This is after a half rotation, right? After half rotation. After half rotation, I find the disk to be at another place. So can you tell me what should be the distance between these 2 points? How much distance, how much of horizontal distance has been traveled?
Sir, pi r.
Pi r. Very good. The horizontal distance traveled should be equal to pi r. Okay. And this is the same distance traveled by the point P. Now in the third one, it again completes half a rotation, and the point is again, point P is again back at the same point. So now again it's pi r, and you have a total distance traveled by it as 2 pi r, which is equal to the circumference. Now during this motion, if I give you a number of, let us consider some of the masses which are located on the disk. So on the disk, I gave you the mass P. Let's have another mass Q. Let's have another mass here R. So do you think that that these masses have also covered the same distance? See, since the point P has traveled from this point to this point, the point P has traveled a distance of pi r, right? But this mass is moving in half a circle. So this mass has traveled just half a circle and its radius is smaller. Can I say that the radius of this mass is smaller? Let's have mass
Yes.
m1. Let's have the mass m2. So m1 is traveling in a smaller radius, m2 is traveling in a bigger radius, and point P is in a still bigger radius. Okay, so I will be discussing two important points for these masses. First point is about their angular velocity. What do you think about the angular velocity and linear velocity of both of them? So angular velocity and linear velocity, I want to compare for all the masses. So for the angular velocity and linear velocity for all the masses, for the mass m1, m2, and let this be the mass m3, which is point P. So you will see that m1 mass, m2 mass, and m3 mass, all the masses, they are traveling the same angle. All of them, they are making the same angle in the same time. So all their angular velocity will be the same. Yes? Any doubts here?
No, sir.
Okay. So
No,
all
sir.
of them will have same angular velocity. Okay. For m1, m2, and m3, all of them are having the same angular velocity. What about the linear speed? Which one is moving faster? Is P moving faster, M1 moving faster, or M2 moving faster?
Sam too.
M2 or P? It's point P which is moving the fastest. It's the point P which moves the fastest. Okay? Since point P, okay, you can see it like this. You can consider a small wheel, a little bigger wheel, and a little bigger wheel. Okay. So if you rotate all the wheels with the same angular velocity, so which wheel will cover the larger distance? The wheel with the bigger radius?
Yes, sir. The larger.
Yes, the larger one. So here the linear velocity of or linear speed of P, that is M3, is fastest. If I compare here linear speeds, so linear M3 is fastest. Okay, and M1 is the slowest. And also during this motion, is there any point which is not rotating? Yes, is there any point which is not rotating?
Center of the circle.
Center of mass. You observe the center of mass, it is just traveling in a straight line. Okay. So see, the center of mass, it is traveling in a straight line only. It's not rotating. So it's the center of mass which is always traveling in a straight line, right? So what important things we conclude over here, that all the substances, all the masses, they have the same angular velocity, but they have different linear speeds. So this is what we call as rolling. When a substance rolls, different masses have different velocities. The masses m1, m2, and the last mass, they will have different linear speeds, but same angular speeds. Okay. And during this motion, the center of mass will be showing just a translatory motion. So I can say that the rolling motion, a motion that consists of a motion that consists of rotation and translation. So a motion that consists of rotation as well as translation, we call such a motion to be rolling motion. And in this, we observe that the linear speed of the center of mass, it is the speed of all the particles. It is the speed with which all the particles are moving. All the particles, they have the same angular velocity. They can have different linear speeds. Understood this much about the rolling motion? Any doubts?
No, sir.
No, sir.
Okay, so we'll do a few questions depending on rolling motion, frequency, and all. Just 1 minute. Giving you some questions. Just 1 minute. Okay. So let's see. Okay. So find the torque generated by a force of 20 Newton acted on a mass of mass 2 kilogram. The force act Okay. So you can start solving. The length of rod is 12 centimeter. So it's something like this. You have a rod and it's pivoted at the center. The force act on it like this at an angle of 60 degree. Okay. So find out the torque. Okay. Who has got the answer? Yes. Anyone got the answer?
So 2.76 torque.
2.76. Okay.
1.3 torque.
For the first one, we should use RF sine theta equal to torque. R we have 0.06 multiply F, which is 20, multiply sine theta, that is root 3 by 2. Okay. So this symbol is read as tau, symbol for torque. Now you can multiply. And multiply and get the answer. Have you got the answer?
It's
1.0.
0.6 root 3.
0.6 root 3.
So 1.
You get 0.
1.03.
Okay, 0.6 root 3 Newton meter. And for the second one, what would be the torque if the rod is pivoted at other end?
So it same, I guess. No.
Yes.
So is it at farther end or the other end? Opposite end.
Farther end. It's written here farther end.
So it means opposite.
Yeah.
Opposite end.
Yes. Okay. So for this, it should be, if it is pivoted at the other end, the only thing that will change is the distance. The distance will become 12. And in that case, you will get your torque to be equal to double of this. And that should be 1.2 root 3. Okay, students. So I hope you have understood about the torque.
Yes, sir.
Okay. So in the next class, we will be discussing about the center of mass of a cone. Okay. Okay. So
Of a coal.
yeah, of cone, what should be the
Okay.
center of mass of a cone, that we'll be discussing in the next class. Okay. Anything else anyone would like to ask? See, currently we are just touching up the chapters, touching up the topics, when we start with the core, so you will be aware of, almost aware of the things. Also here, since for linear motion, we have done force equals to mass times acceleration, right? So here, mass is called as the inertia factor. Mass is the inertia. In the similar way, for the rotation, we have torque given by I times alpha, where alpha we call as the centripetal acceleration. Not centripetal, it's the circular acceleration or angular acceleration. So alpha is the angular acceleration and I is the inertia factor. I is the inertia of rotation. So once we start, we'll be going into the depth of it. I, inertia of rotation, also called as moment of inertia. So that's why almost all the things are similar. We'll be studying this rotation in a few days. Okay. So bye all of you. See you in next class.
Yes, sir. Thank you, sir. Bye, sir.
Thank you, sir. Have a nice day, sir.